Okay, so I'm going to use my circle tool. I'm going to create a circle, and I'm not interested in that point B. I'll leave point A there. I'm going to place a couple of points on the circle. So let's place these points here, C and D. Now, if I make a segment that has its endpoints on the circle, inscribed on the circle, like C and D, and its other endpoint is the center of the circle, we call that endpoint a radius. So a radius, we call that segment a radius. Radius is a segment with one endpoint inscribed on a circle and the other endpoint at the center of a circle. And sometimes we call its measure, the radius of a circle. So in other words, that term gets used, the term radius gets used a couple different ways. It gets used to describe the segment itself, and it also gets used to describe the radius or the measure of that segment. And that's because it's a property that's unique to that circle. Whenever we have a circle, its property is that all of these points are equidistant. So all of these radii, which is the plural of radius, all of them have the exact same measure, and that's the property, right? So these segments here are equidistant, or they're they're equal measure, okay? So now let's talk about these two angles. If we take, or these two segments here, if we take, let's say when we take two radii, that's radii, the plural of radius, okay, so when we take two radii, we form an angle called a central angle, which makes sense, right? Because the vertex of the angle is at the center of the circle. Well, let's see how that looks here, okay? So we take two radii like AD and AC. Now we've got an angle called a central angle, and that makes sense because the vertex of this angle, DAC or CAD, the vertex right here is point A, and that is the center of the circle. So that's what we call a central angle. So let's go ahead and measure the central angle for a minute. CAD, in this case, measures 88.17 degrees. But if I move D, we're just going to continue to measure it. Now I want you to look, think about, this is a very small angle, right? 4.68 degrees. How big can this angle get? Remember, it can get obtuse, and then it can get even larger than 180 degrees. It can go all the way around. What number would it reach? Just take a look there and make a prediction. 350. Whoa, it goes back to 0. 359.6. So a central angle can measure up to 360 degrees. Okay? Now this brings up, the part of the circle that we're measuring here. So right here in this case, we have this part of the circle from D to C is called an arc. This is an arc from D to C, and this is called the minor arc. Okay? So with an acute central angle, the portion of the circle that lays between that acute angle is called the minor arc. Okay? And actually that's for any angle, even includes obtuse angles. This would be our minor arc, as long as the central angle does not measure 180. When it measures 180, now we have exactly, now this is pretty close to it, but this would be a semicircle. It would take up half the circle, right? And so then that is not even called an arc anymore, it's called a semicircle. Okay, and when we get over 180 degrees, then this part of the circle is called a major arc. So you have a major arc, and then you'd have a minor arc. So really every central angle, creates two separate arcs. with the only exception being when we have a central angle that measures exactly 180 degrees, which we're pretty close to there, and then neither of these are called arcs, they're just called semicircles. So what is it called when we have, 180 degree central angle? Well, we're going to use another term for that. So we're putting in a lot of terms here, but we're going to talk first about what a chord is. A chord is a segment with end points on the circle. Okay, so in end points we'll just say inscribed on the circle. Okay, so that's what a chord is. So if I were to connect, let's see if we can make a chord here. If I were to connect endpoints that are on the circle like DC, now we have what's called a chord. Okay, that's a chord. Now as I move this around, if I get it to where it goes 180 degrees, guess what that chord is doing? It's going through our center. Okay, that's what it's going to do. So let's use our definition tool here again. Let's say a chord that goes through the center of a circle is called a diameter. It's a special chord, goes through the center of the circle. It's called a diameter, right? And we can see one pretty close to one here. That's not quite, but it's very, very, very close. Okay? So then we have major arcs, minor arcs, okay? And we have semicircles. All right, let's go through a few other things. Let's talk about a line that goes through the circle. So we'll just make a line here. So a line that just goes through the circle. That has a term that we want to know. A line that goes through a circle is called a secant. And it touches the circle in two places. Okay? If it's going through it, it has to have a point where it enters the circle and then travels within the circle, then a point where it exits the circle. So that's a secant. Okay, so a chord is a part, it's a segment that would be part of a line that we call a secant. Okay, now the next term that we're going to do, and this is what happens, I want you to think about this, when a line touches a circle not in two places, but a line that touches a circle in exactly one place. So a line that touches a circle in exactly one place is called a tangent line. Okay, that's what that's called. And the point, we'll put this in here, and the point where it touches is, let me change that to a comma there, is called the point of tangency. Okay, so a line that touches a circle in exactly one place is called a tangent line. So let's see if we can construct a tangent line in our constructions here under circle. Now where are we going? Oh, here it is. A tangents. So we're going to pick the circle and then pick a point that is not on the circle. Well, let me first, I guess I need to construct a point. Let's construct a point over here. And now we can use our tangents to say, give me this circle and that point. And you can see that what we have is we have these lines that touch this circle in exactly this point. Okay, let's find that exact point using an intersection where this line intersects that circle is point H, where this line intersects that circle is point I. So now you can see that this line, CH, is tangent to circle A at point H, and CI is tangent to A at point I. Okay, and now we have something that's another angle. Okay, so here we go. We're going to do another angle here. So another angle that is formed, it is, oops, sorry, is the I don't know what's going on with my mouse. Sorry about that. Is the circumscribed angle, which is the angle formed where two tangents intersect. Okay? So, a circumscribed angle. This is the circumscribed angle. It's the angle formed where two tangents intersect. So let's just make sure we're clear on that. So there we have a tangent. Now we have a circumscribed angle. It's built where these, intersect. Okay. Now, remember, there's one more angle here. It's really an important one, and that's the one. Remember that we talked about chords. So what if I place, let me get another point here, just another point on the object. Let's just make it that point J. So what if I were to place and make chords, right, here and right there. I'm going to get rid of that chord there. I don't need it. So then what I have is I have an angle that is formed when two chords have a common endpoint. Okay, now remember that chords are segments with endpoints that are inscribed on the circle. So let's do this again. So there it is. Chord is a segment with endpoint inscribed on a circle. So when two chords have a common endpoint, they form an angle called an inscribed angle, which makes sense because the vertex of the angle is inscribed on the circle. Okay, that makes sense. Let's see what that looks like. We have angle, click off to the side here. We have angle CJD is an inscribed angle. Okay, we have an inscribed angle CJD. It's inscribed here, and it is two chords. We have chord JC and JD, and they have a common endpoint, which is point J, and it is inscribed in the circle. Okay, now I want you to notice there's a relationship between the central angle and its inscribed angle. Watch what happens when I swing this around. Turns out that this angle here, the inscribed angle, is equal to exactly half of the central angle. And it doesn't matter where that angle is inscribed at. Notice it's always 50.37 here. Right? Moving this vertex won't change a thing. Okay? The only thing that'll change it is changing the angle here. But I notice that whatever I've got here for my inscribed angle, my central angle is twice as big. 2 times 18 is 36, and 2 times 91 is 182. So now we see that the central angle is twice as big as the inscribed angle. That is a huge relationship to note here. A central angle is always twice as big as its inscribed angle. Okay? And of course that means that an inscribed angle is always half as big as its central angle. Those will be important to know when you're wanting to solve problems. Okay? If you know, they'll give you the central angle here, and they'll say, oh, the central angle is 161.32. What is this inscribed angle? And you'll say, oh, wait a minute. It's half of 121.32. So 121.32 divided by 2. In your calculator, you get 60.66, and you'd be correct. Okay? Now, the last thing I'm going to show you will be the relationship between a tangent and the radius at the point of tangency. So let's analyze that. I want you to notice what happens if we create a radius from, that's obviously a segment, to a point on the circle, right? And, oh, that's not the one I wanted. Sorry. What we're going to do is create a radius to the point of tangency, from the circle, center of the circle to the circle point where it's tangent. Okay, I'm going to do it here with I. And what you're going to notice is that when we measure that angle, okay, let's try it here. Oh, going the wrong way. Let's try it again. So here we go. We've got this angle here. It's a 90-degree angle. And that makes a lot of sense, because if it were anything other than a 90-degree angle, think of this like a teeter-totter, right? If it tipped a little bit this way, it would go back inside the circle. And if it tipped that way, just a little bit, if it was greater, this angle was greater than 90, then it would force this line to tip inside the circle. So it's got to meet at exactly 90 degrees on either side. Okay? That's going to come up a lot when you have things like polygons. When you have, this quadrilateral that is formed, okay, looks a lot like a kite between these 4 points, the center of the circle, the 2 points of tangency, and the intersection point of these tangent lines, so that we have the circumscribed angle. There's a relationship between the circumscribed angle and this angle here, this central angle that is formed between the two tangent lines. So let's measure that out. Ready? Watch this. We'll measure angle IA. Oops, let's try it the other way. Let's measure angle HAI. And you can see that it measures 130.37 degrees. So what happens is, if you add these two numbers together, they equal 180. And that's important because inside of every quadrilateral, there are 360 degrees. If 90 is here at the point of tangency, 90 here at the point of tangency, these angles opposite each other must be supplementary. Okay? Even if I move that point around, that angle, those two will always add up to 180 degrees. Okay? You make that a wider and wider angle there, 152 point, oh, let's move it back in. 150.05 and 29.95. Add that together, 180. And notice that these two remain, right angles at all times. They always remain right angles. That's very, very, very important to know. Okay, so that's the basic overviews about the different types of angles that exist with a triangle, and the relationships between central and inscribed angles, right? Central, here's a central angle here, here's an inscribed angle, it's related inscribed angle. Tangent lines and the radii at the point of tangency form right angles. And the circumscribed angles have a relationship to, and that they are always supplementary to the related in central angle. Okay, and that's the information you need to know.